Okay, bear with me 1 second. I'm trying to share my screen and pull up the syllabus. Okay, so I assume you guys can see my screen now, right? Okay, great. So yeah, um, so I just want to quickly go through the syllabus first, and then we can discuss the topics for the first 2 weeks. First 2 weeks in general, the modeling methods are more straightforward. So hopefully it doesn't take a lot of time for you to review the contents. So if you can see, I hope you already get a chance to read the syllabus, but if not, we can walk through together. So if you look at this, first of all, the whole purpose of this course is really laying down the foundation for math modeling techniques. So it has a combination of multiple modeling methodologies that it's meant to be useful in many other methodologies or different courses down the road. That would be really helpful. And then, for example, later you would study linear regression in further detail, and then you would realize that some of the math fundamentals for linear regression is coming from this course. And then you probably would be learning machine learning, for example, support vector machine. Support vector machine as one of the regression methods or as one of the classification methods. It is really a quadratic programming a nonlinear programming model. So in this case, if you look at here, what we are going to discuss here, K modeling methodology would include something such as integer programming, nonlinear programming, quadratic programming, differential equations, and some simulation. Simulation is really just a brief introduction. And on top of that, we have game theory and decision theory. So it's more like a breadth of the coverage. It does have a certain level of depth already, but I do feel like it's an important topic to understand. In reality, I spoke to a couple of students after graduation when they're trying to land the first job. This course turns out to be some of the key concepts, one of the most popular questions that employers would be asking. Why is that? The reason that because I think my understanding of this is because when you are fresh out of school, um, uh, yes, you probably have some sort of experience, but the majority of the time your experience would not be as relevant. And then what's really important becomes how good your understanding of some of the key topics is. This would help you to land that job. And then I would say that it happens that including computational mathematics that you probably have already studied, and also this course tends to be important foundation courses. And then after this, of course, data mining, predictive analytics, and even machine learning would be useful as well, but tends to be more application oriented. And then maybe future employers would be asking things such as what kind of project you have done and whether you did some interesting projects that showcase that you have used some of the methodologies. Okay, without further ado, so long story short, we're trying to learn some math modeling techniques from the formulation perspective and also from the solution perspective, from computational perspective. And then, of course, we want you to try to understand what's the difference between model or simulation, and how do you go through the whole process, such as try to understand data, try to collect data, and then try to model the data, and then try to do some sort of modeling implementation and deployment, and then trying to understand the results. And then going back, how potentially you can improve your model. As you can imagine, all the modeling process would be an iterative process, and also there is no unique and single solution for any of the problems that's out there. Of course, some of the problems would be probably, if we have 5 people, would probably have one solution. That's also at least one solution methodology. But many times what happens is, for one problem, potentially we could have multiple solutions, multiple methodologies. Hopefully at the end, the conclusion would be the same. Majority of the time it is, because it really depends on what type of assumptions you have made for coming up with a solution for the problem, and then what type of simplification you have made. We may have different results, and hopefully at the end of the day, conclusions would be the same. Okay, so again, why we think it's important, again, it's analytical, and it's the foundation for many of the data analytics methodology. And of course, 3 years down the road after you graduate, after you land your first job, you probably don't think some of this methodology would be as useful, but you would never know, because what happens is, when there's a problem, you're trying to figure out a solution. Once you realize you have all of these skill sets in your hand, you probably can help you to think through some of these problems, and then you can go back and dig some of these key concepts a little bit further. So hopefully that can help you to solve those problems. Okay, here we go to the assignments and grading. So we have 12% being the participation, basically participation, and basically this would be your not weekly, bi-weekly discussion on the discussion board. So I'm saying that one substantial discussion every 2 weeks, which would be, I'm expecting like 6 discussions, plus week 0, which is prior to today, or what is happening today as well, getting to know you. Hopefully you can finish that by the end of week 2. So in that being said, so we have 6 discussions, and one of them would be week 0, and then the other 5 would be from week 1 to week 10. Every 2 weeks you have a discussion topic. So essentially by the end of week 2, you already finished 2 discussion topics, and then you got 4 points essentially. And then I encourage you to to have this discussion spirit there, not just, oh, I want to talk about something and then no one responded, unless no one is interested in. So I want to encourage you guys to have more interaction, communication, and discussion through the forums. And this is one way, using this 12% of the grids, to encourage you to do that. And then you can see that we do have 7 assignments. If you think about it this way, it would be first 14 weeks. You probably every 2 weeks you have a homework. So you have 7 homework. Each of them is counted as 9%. So you have 63% of the assignments, and then the rest of them would be a course project. And then I also, for the assignment, I want to mention that you only need to finish 4 or 2 of selected. Only have this or 2 just because of the last homework only have 2 problems. And then the first homework have 4 problems because it's 2 weeks, right? First homework would cover week 1 and week 2, and then essentially you would be selecting 2 from week 1's topic and 2 from week 2's topic. So you would have 4 selected problems that you would finish for 1 homework, except the last homework you only have 2 instead of 4. And then I don't grade all the homeworks, but I will share all the homework solutions. It's by no means the best solution. It's really just using it as a guideline so that you try to understand. You would help you to understand the problem, to see if you are thinking from a different perspective from the solution, and then I definitely encourage you to go through that solution. If you have anything, any doubt or any questions about the solution, we can always discuss. And then if you prefer, we can even discuss in class with everybody as well. So that's what that is. And cost project works for 25%, and then you have to finish proposal by the end of week 10, which is 10% of the project grade, which is essentially 25% times 10% to 25 points. And then presentation slides would be due in week 15 by end of the day of the presentation day. Presentation day would be week 15 Tuesday 7 p.m. And then it was 10% of the grade, but you should submit those presentation slides by the end of that day. And then presentation starts in week 15 class was 30% of the grade, and then you could submit the final project report by the end of the week 15. And then we do have some discussion about the project at the moment. I can go through all the way. At the end of this syllabus, you would see the last page, page 5. You can see some discussion there. So what I'm trying to do here is, because we have a breadth of all types of methodologies that covered in this course, I hope you would be able to have a chance to apply 2 of the methodology that we learn in class into 1 problem. It could be any phenomena or real problem or real world or real business problem of your choice, and then apply 2 methods. It can be simple as simple as a linear regression. It can be linear regression is simple, but it can be very involved as well. And then it can be a simulation method. It can be an optimization. It can be some sort of game theory, or it could be some decision theory related methodology. So you can apply 2 mathematical techniques to the problem, and then I encourage you to work on the project with 2 people, with 1 people. So essentially, a team will consist of 2 members. You can also choose to work on the project by your own, just because of the reason that you're not able to, your schedule doesn't match with anyone else or things in that nature. Then you can work on your own as well. Of course, if you say, okay, 3 of us are interested in a very similar topic, then we want to then I would encourage you guys to form a team of 3 or 4. That would be perfectly fine as well. Hold on 1 second. Oh, 他没告诉我。我要签53节45结束。现在哪点？啊？现在几点？现在20。这是唯一啊，对吧？那你怎么办？他已经来了。真的，在家。你说我现在。现在45结束。对，让他坐一会儿。对。Okay. So regarding this team, right? If you are, I'm saying that if you are a team of 2, you can try 2 methods. If you are a team of 3 or more, you can try 2 methods as well discussed in class, but hopefully it's more depth of analysis. And then in terms of the project schedule, you can form the team by end of week 10 and submit proposal by the end of week 10. And then it's worth 10% of the project grade, and then everything else I already discussed. But the thing is, you want to pay attention would be the presentation would be less than 5 to 10 minutes, and then the report should include these key elements such as analysis of the problem, the methodology you used, detail of the methodology, the findings from the project, and are they different from your initial expectation? If so, is there a suitable explanation? By no means that you should address all of them, but you should at least address some of these problems. And then the report can be very compact. It can be like 3-5 pages with some sort of appendix. You don't really need to spend a significant amount of time to write the report. So that's a report part. So if we come back to the general plan, here is the plan, and then for example, we will follow this very rigorously. For week 1, we briefly discuss what is modeling, and then week 2, the modeling process, etc. And then by the end of the week 2, you would have a homework 1 due, right? And then for example, today I would right after discussion of syllabus, I will quickly cover week 1, week 2 slides, and then hopefully give you a guideline on the topics, so that you should spend some time to read the textbook, chapter 1, chapter 2, this week and next week. And then by the end of the week, you should find out that the homework is really an application of the detailed techniques that you read in the chapters, and then it's very straightforward. But definitely, it's worthwhile for you to work through the problem so that you realize you understand the concept and know how to apply the methodology. Okay, so this is really the gist of the syllabus. I want to stop here for any questions if you may have. Good, how are you? How are you, Duda? I'm not sure if it's exactly the same. I assume that some previous students actually took the Asian version. Okay, Kay already found a solution. So if I assume it should be the same, I don't see any difference. Okay. Any other questions on the syllabus? Okay, if not, give me 1 minute. I get some water, and then we'll continue with the discussion here. Okay, you guys can hang around for a little bit as well. Just 1 minute. Thank you. Okay, so I'm back. So let me continue with the with the slide. So as you can see here, we call it module one. So essentially, it is the first week uh, first week material. So first of all, I just want to remind you. Um, oh, by the way, if you know, because you need to read the textbook, otherwise you wouldn't understand some of the key concepts there. Just because it's a I think the textbook is well written, even though it is kind of expensive. Hopefully, after this course, you would try to sell it on Amazon or somewhere. But it is definitely worthwhile to have the textbook. You would realize that it's well written textbook and has a lot of good stuff in there. And and uh, um, so what I want to say is you should get your textbook as soon as you could, because we do have a homework due by the end of next week. If you're not able to get a textbook before that, definitely send me an email. I potentially could delay that for another week, which because I cannot delay too much because the other homework would be due in another 2 weeks, right? So I won't be able to delay too much. At least I would be able to grant you another week of time so that you would be able to finish the homework. And then, first of all, I want to mention once you get the homework, first thing you want to do, review some of the basic integration techniques. We don't use that technique right away, so you can take your time to review that Appendix D. But by the end of week 4, if you reviewed everything in Appendix D, then that should be sufficient. It's a basic integration techniques such as separation of the variables, such as some of the basic calculus that you learned in college. So once you review that, make sure that you are comfortable with those math techniques, and then along the road, ask questions if you have any, so that we would be able to help. I would be able to help you to understand some of the concepts, and then these would be used for some of the differential equation related modeling techniques. Okay, so these were the key concepts in Appendix D, such as U substitution, integration by parts, rational functions, and partial fractions, things in that nature. And then, for example, in quadratic function, how can you find the minimum number and minimum corresponding solution? That would be something that potentially will be discussed there as well. And then in terms of chapter one, what we discussed there in the textbook is really concept is simple, trying to model the change, and then how to model the change with difference equations. Here you can see it's called difference equations. It's not differential equations, but differential equations coming from difference equations. And then let's look at what is difference equations, and then how we potentially can use this simple methodology for some of the problem. So, and then before we delve into that difference equations, I want to give you a high level of understanding of what is a model and what's the purpose of the model. It's somewhat simple, but you can think through this process. Once you have a real world data, you're trying to simplify this data, try to build a model, and then you run some analysis on the model, you got some sort of mathematical conclusions. And then you try to use this mathematical conclusion, try to interpret the results. You have some sort of either explanations or some sort of predictions of the future. And then you collect more data from the real world, and then try to verify whether your model or prediction is correct or not. That's all kinds of model has to go through this process, right? So that simple process, even though it looks simple, but in reality, a lot of models can be complicated. A lot of processes can be complicated. Even getting the data itself can be can be a difficult task. Okay, so in this case, let's see how can we modeling a change. First of all, if you look at the definition on the top, we can see that y and x are proportional just because y equal to kx, for example, and then x is y's movement is related to x, then we say it's proportional. And then what is the we also write this as this y is related to x for a non-constant k. And then how can we model change? Change is really that future value equals to present value plus a change. This is a difference equation. If you think about it, it's future value minus present value equal to change, right? So this is just as simple as that. That is a difference equation. And then let's say very quickly, how can we apply this? And then for sequence of numbers, A0 all the way keep going. And then the first difference is delta A0 is A1 minus A0 and all the way keep going. And then for each positive integer n, the nth of the first difference is delta an is an plus 1 minus an. So that is n's first difference. First difference essentially meaning today's value minus previous value, only one period difference. That's why it's called first difference. Not necessarily time related, but it could be a sequence of numbers as long as current number minus previous number, that is called first difference, right? And then what does this mean? So what we are saying just now, I just said for one period time, what is the y value change? Suppose that in two-dimensional space, x-axis is n time epoch, and then y-axis is a corresponding value, and then we get n, a sub n, versus n plus 1, a sub n plus 1. And then we know with this change of one time period change, the value change of the y is delta an, which is an minus 1 minus an. That is the first difference. Okay, it's simple graphical representation. And then see how can we use this for modeling something like mortgaging a home. Suppose that your initial for your loan initial value is 80,000, and then we know the value as time goes on. It's loan value. The balance of your value follows this relationship b sub n plus 1 equal to bn plus 0.01 bn minus this number, and then we would be able to draw this line. We say, okay, at the end of 232 months, you would be able to pay off your balance. This is one way to look at the application. Again, it is a first difference, except that here you can see there is a little bit change. B sub n plus 1 minus bn is a function of previous balance. The difference is a function of previous balance. Okay, and then we want to say that a dynamical system is a relation among terms in a sequence, and a numerical solution is a table of values satisfying the dynamical system. Even though it's all definition, but it's straightforward. And then if we think about this, if we think about how we can approximate the change. So we say that the change is delta a sub n is some sort of function. If we look at the discrete case on the bottom left, x-axis is timing hours, y is east biomass, and then you can see that for different time epoch, there will be a different east biomass, and then the question becomes, how can we model this process? Would we be able to use this difference concept to model it? The solution is the answer is yes. You can say that delta Pn, which is Pn plus 1 minus Pn, is half of a previous east biomass. So that is meaning that every period it just decayed, right? The mass just increased. So essentially, next period of mass is 1.5 of previous current period of the mass. So that is one way to look at it, which is happen to be a discrete, and then it also has some sort of upper bound when it approach like 15 years and beyond, it's kind of stable somewhere. And then looking at the graph on the right hand side, you can see that this is growth constrained by resources. Just because of the resources constraint, you can have some sort of continuous change modeling, and then that delta change is k times a constant minus Pn times Pn. And then in this case, you can see that the relationship is no longer linear. The delta difference is a quadratic function of current Pn squared basically. So delta Pn is quadratic of Pn, which is Pn squared. What I'm saying, quadratic. Okay, so that is something interesting that you should pay attention, because later on in the course we talk about linear program. We're dealing with specifically linear relationship, but here on the right hand side, bottom right, you can see it's quadratic. Okay, and then the question becomes, are we able to solve this numerically? Are we able to try to come up with a solution, and we try to predict, and how good that model is? For example, here you can see the black dots are the observation, and the circle dots are the predictions. It's not too bad. It's not too far away in this scenario. Just give you a flavor of what we meant in terms of modeling. And then so we want to see that how can you solve that problem? You know, for any sort of problem that you have, what can we do? You want to look for a pattern. You want to come up with some sort of conjecture right after that. Oh, this one looks like linear relationship, and then I can model it as a linear. And then you use some sort of statistics to test, is this really linear? And then if it is linear, you come up with a conclusion. Yes, it is linear, just because I tested with statistics, sufficient evidence, statistically speaking, sufficient evidence to support my conjecture that it is indeed a linear relationship. Okay, so that is the method of conjecture, powerful mathematical technique to hypothesize the form of a solution, and then try to accept or reject the initial hypothesis that you had for that problem. And then for linear dynamical system, that is no longer a difference, is no longer a constant, and then we're saying that previous number is r times, next number is I times previous number. Or let's think about current number is I times previous number. And r is a non-constant, non-zero constant. And a0 itself is a given initial value. And And then we also talk about equilibrium values or fixed point of the dynamic system. That is, if we find a value of AK equal to A for all of the K, all the sequences, then when A0 equal to A, then we say that AK equal to A is a constant solution for the dynamical system. So it looks difficult to understand, but let's look at the theorem too. So the idea is if n plus 1 equal to RAN plus B, and then the equilibrium value for this solution is really that A is B divided by 1 minus N. So that is, if you remember some of this linear relationship there, you know that essentially saying that if n is approaching infinity, this solution that we saw here is really the solution for this problem, right? And then for different ones, say for the next one we say, okay, if so the solution for this system is AK equal to R powered by K plus B divided by 1 minus R. Okay, which depends on the initial solution condition. And then we quickly discuss the nonlinear system. That is to say that current value is a nonlinear relationship of previous value. You can see here the current value is A sub n plus 1. The previous value would be A n squared. That's why this relationship does have a nonlinear relationship there. And then in the textbook, there are some very good examples of difference equations. Especially, I want to point you to the first one because this one would be used later on in the course as well. So you should definitely read all of them, but pay attention to the first example, a car rental company, how we use difference equation to solve that car rental company problem. Yeah, as I said, some of these examples will be discussed later using different methodology, but here you should try to understand these examples, try to understand what the problem is, how did we come up with the solution, and also pay attention to the sensitivity of the initial solution, which is how stable the solution is from the model. Okay. And then this is the homework for chapter 1. So you only need to pick 2 out of this list for the first week, and then you pick 2 out of the second week list for the second portion. But you put them together, submit homework 1 by the end of week 2. Okay, that's what I want to discuss for the first section. Any questions? Module 1. Yes, absolutely. That's why you read the textbook, send me emails if you have questions. We potentially could also discuss when we meet again 2 weeks from today. Even though it happened that 2 weeks from today is September 11th, if I remember correctly. Actually, somehow they said class, we don't have class on that day. We'll figure out. I'll send you an email. Even if we don't have anything, I will try to give you some video. You would be able to listen to some of the concepts. Okay, for module 2, it's still very similar than what we just discussed. It's just use how to model, use proportionality, or use geometric similarity. So if we think about this example that we just had, again, for real-world problem, we try to observe the behavior of phenomena. You can look at the difference between the left and right-hand side. Right-hand side is a mathematical world, and left-hand is real-world problem. You can look at the bottom 2 charts. You can see the difference is really that on the left of this of this charts, which says we come up with real world behavior. We have multiple trials to get a real world conclusion. But in the mathematical world, we use real world explanation or predictions to verify the real world data. So that's really the key difference between those two. And then why we want to use a math model is just because we think certain behavior can be simplified. Certain real world behavior can be simplified by a math model, and it's so generic that it can be used for any sort of explanation and prediction. Of course, as time goes on, as things change, as data collection process change, new data came in, you could refine your model. Doesn't mean your model would work all the time. And then later we would see that the key difference between simulation and the math model, which actually would, I think it's the next slide. So for example, let's look at this. If we think about a phenomenon of interest, we could have some sort of mathematical representation. We could also have replication of behavior. So which is the previous slide we discussed two difference between the trials and the math model. So that's two branch. If you look at continue with the first graph, on the top you can see from math representation you could have model construction, you could have model selection, but in the replication of behavior you have to do some sort of experimentation, get all kinds of trials, or you could leverage computer to do some sort of simulation. And then what's the difference between all of this methodology? If let's look at from 3 dimensions, fidelity, how good the model or the methodology represent the real world data, or from the cost, how expensive that would be, or from the flexibility perspective, how easy that can be customized, can be changed, right? As you can see, for math models, it would be more flexible because it's once you build a model, you can use it, hopefully use in a real context, right? And then the cost is not too high just because you don't spend a lot of time to do real world data collection or experiments. It can be very expensive if you collect real world data and then try to do experiments. It doesn't mean that we don't need data in mathematical models, but in terms of comparison wise, you don't need a lot of data if you don't you are building a model. But if you are trying to do real world trials, you need a lot of data to do that. And then of course, if you have more data, you have more fidelity to the real world. On the left hand side of this chart, you can see that real world observation have more fidelity of the real world, and experimentation actually followed by simulation. And math model probably have some sort of simplification, some sort of assumption which made it less representative to the real world. But it's always a trade-off, right? So once you decided to go to the math modeling world, you realize as long as you know the assumption and disadvantage of your model, that would be the key for your defending your results. It's always when you talk to the business, you say, look at this model, it comes with this, you would be able to explain that results. It's not like you say, okay, here is the model, look at the results yourself. That would be something really that insights would be really important for anyone who is trying to build a model. Okay, here in terms of the solution methodology, I want to point out that it is really a iterative process itself. You identify problem, make assumptions, solve the model, verify the model, implement the model, and maintain the model. But it's iterative in the sense that once you implement, you go back to see whether it's doing well when you in the maintenance process, whether the model is doing well. If not, go back to think about whether your assumptions have problems. Okay. So here, another perspective, we want to see that, the art of the math modeling is really simplifying or refining the model. it's definitely required. And then you have to simplify it, you have to refine it. And then in simplification case, you want to neglect some of the variables, and then you want to restrict problem identification, all kinds of possibilities that you can assume may be a simple or linear relationship. But in the refinement stage, you want to expand the problem, you want to consider more variables, you want to think about different variations of the variables. So it's a trade-off between those two, but the majority of the time you want to start simple, think about something simple, and then start build upon that to expand the simple model to a more complicated one. And then in terms of this concept, proportionality, could be a lot of proportionalities that you have studied in high school physics, such as Hooke's law, Newton's law, Ohm's law. All of this theory of and Einstein's theory of relativity and Kepler's third law, all of them are proportionalities, right? And then in chapter 3, which would be a next topic we can discuss 2 weeks from now, would be on the theta linear model. And then in terms of geometric similarity, in the example 2.4 and 5 have very good case studies on raindrops. And then I think you should pay attention to the first example, even though here it has 3. So I give you some highlights. If you have time, read through the whole thing. If not, at least read the first example. And then here is a homework for the second week, which would be for next week. And then you can select 2 out of this list and combine with chapter 1, 2 together. For of them, you can submit 1 homework, which is homework 1 basically, which is due in by the end of next week, which is Sunday 11:59. Of course, as I said, you have to let me know if you're not able to get your textbook on time, and then we can extend that to the end of week after, which would be September. Would be September 9th. No, September 16th. Okay. Any other questions? So you guys, if you have any question, send me email or ask from the black box system, and I'll try to respond at my earliest convenience. And then hopefully by the end of semester, I hope you guys feel that you learned something from this course, because I think it's an important concept, and it would be useful down the road as well. Okay. Thank you. Question, is each homework due on Sunday? Yes, each homework is due on Sunday 11:59 Eastern Time, and I said end of week, which essentially says end of Sunday, which is 11:59. Okay, sure. Thank you, and then we could stop here, and I hope to talk to you again very soon. And if you have questions, send me emails. Okay, bye bye.